We are going to have our lecture this day for the topic on momentum. So this is the last lesson that is included for our first quarter exam coverage. And aside from momentum, there is a similar concept that we are going to discuss as well, which is called as impulse. So let's begin with the idea of momentum. Now, momentum, if we are going to use the dialect, no? So if you have a vehicle, if you have somebody that is running or moving, no? Now, if you intend to stop it from moving, then most likely you have to anticipate, no? How much, no, is the momentum of the body, no? Are you able to keep it, no, or stop it, or will you both, no, roll together when you come into contact with one another, no? So in the dialect, probably we can call the word momentum as the word boilo, no? Amo na ang aton sa Ilonggo nga word, no? When the car, no, is running, no, mayara na siya ginatawag nga boilo, no? So if you intend to stop the car that is moving, no, when you come in its way, no, then a lot of possibilities could happen. If the car will not be able to step on the brake, then most likely, no, you'll get hit by the car, and again, no, there are so many possibilities there, no? So when you're run over by the car, no? Now the mass of a body, no, or a given body, no, is a measure of its inertia, no? That's what we learn from the law of inertia, no? So bodies with greater masses will tend to change, no, rather more slowly, or it will take time for it to change. So like when it is at rest, then you will really have to exert a lot of external force to make it move. However, when the body that is already moving, no, when you tend to stop or slow it down, then you'll have to also, no, kind of come on its way, no? You have to apply an extensive force also to make it slow down or come to a stop, no? So again, no, somebody or similar to a car that is running on the road and hitting, no, somebody on the road. Now, the more mass a body has, no, the greater is its tendency to stay at rest. If it is at rest, no, or no, it will keep on moving, no, once it is already moving, no? So it will be quite difficult for something to moving to that you intend to stop, no, from moving. Like a huge boat, no, on the dock, no. So let's say, for example, a huge boat that is trying to maneuver, no, and dock on a certain pier, and for some reason it will lost control. You will realize that huge ship, no, once it hits the pier, no, then it will create a lot of damage, no? So again, no, by the mere mass of that huge ship, no? So ang builos ng dako nga barko will be so much, no? Again, not talking about momentum, and we will see some factors that are affecting, no, the value of the momentum. So again, in the Ilonggo word, momentum is ang builo nato, no? Now we can see probably, no, the momentum of this elephant and the momentum of this person, no? Maybe they are side by side, but which one can you probably, no, let's say the elephant is resting, no, and the person is also resting. If you try to move, no, one of them, no, which one will be easier to push or to roll, no? So I think, no, an obvious answer would be the person, no, the guy, no? Because the guy is smaller, less massive, no, than the elephant, no? If you try to push, no, an elephant that is lying, no, on its back, it will be very, very difficult to even move it an inch, no? Because again, no, by its mere mass, no? So the massive body, no, tends to stay, no, at rest compared to a less massive body. Now the elephant has more, no, inertia than the human being. So this means, no, it's harder to change an elephant's motion than a human being's motion. So we have, no, another idea here, no, which is the relation of inertia, no, and the motion to and motion, no, to momentum. So what is the effect of inertia and motion to momentum? So momentum can be observed, no, in our daily experience, no? So the greater the linear momentum of a body, the greater the effort no, needed to change its path, no, or to stop the body from moving. Now, just imagine this prime mover. Now, we call it a prime mover. Now, this is a huge truck. No? It carries no, this container behind it. No? Now, this prime mover, no, this car in front here, this is the one that is merely moving, no? And behind it no, is merely a container. No? Maybe it's empty or not. No? But again, no, this one, once this is on the road, no, and it encounters a collision on the road, then you see, no, in cases where they run no, on U.S. roads, no, on highways, and they encounter an accident, no, you'll notice that it's going to be a pile up of vehicles, no, because again, no, you cannot just simply stop this one, no. Once this one lost its brake, no, or its control, then once it hits no other vehicles, then most likely no a pile up will happen. No? Many other vehicles will be affected because it's so difficult to stop this one no, once this huge car is already in motion. Now, linear momentum no, is the product of two things. One is mass, and another is the velocity of the object. So if the object has a greater velocity, then its momentum will be bigger. No? If you let something no, move a little bit slower, no? less velocity, no? Then you will also see that its momentum will be kind of lesser. No? Now, another factor there is mass. The more massive is the body, then it will directly affect the momentum. So bigger mass means greater linear momentum. Again, ang sa Ilonggo, kaning word natin sa momentum no, is boilo. No? So kung ang dako nga truck, no, and you have a small car beside it, no, so obviously, no, if they run at the same speed, then this huge truck will have a bigger momentum, no, more difficult to stop compared to a smaller car, no, that is traveling at similar speed. No? So again, two factors that affects our linear momentum: mass and our no, velocity. No? Now, if you multiply mass times velocity, we will end up with a unit kilogram meter no, per second. So if you recall, no, we have a unit kilogram meter per second square last time, and that unit is equals to your Newton. No? But this one, the unit of time there is merely seconds. No? So it's not second square. So that's our unit of momentum, kilogram meter per second. Now, in this way of writing our formula, now we can also recall that when we solve for P, then we will be multiplying mass times velocity. No? But if we will solve for mass, then we will be dividing no, the value. No? So P, or momentum, divided by the velocity. No? And likewise, your velocity no, could also be equivalent to momentum divided by the mass. Now, the greater the mass no, and the velocity of the object, no, the more difficult it is no, to change the object's speed and direction. Now, look at this huge truck no, that is making a turn. Now it hits this parked car no, beside it, and you notice, no, even though the other car no, was dragged, no, the huge truck no, did not change its speed no, or even its direction. No? So it simply dragged the other smaller car. No? Again, no, by the mere momentum of this huge truck. No? So again, no, I think this is also a prime mover. No? So a prime mover usually no, carries with it no, huge masses, but therefore its momentum is so big. Now, momentum is a vector quantity, no? So it's affected by its velocity. That's why the momentum can be likewise considered positive or negative in its value, no? Because it's considered as a vector quantity. No? If you're going to compare a small car no, and a massive truck no, at the same speed, no? The small car, since it has no, lesser mass, has smaller momentum compared to the truck, no? Because the truck has a larger mass. No? So we have here Mr. Bean no, riding his small car. No? So the car here of Mr. Bean probably no, has lesser momentum no? Because it is relatively lesser in mass. No? Now, a shipping vessel or a ship no, out at the ocean, no, can have a large momentum, no, even when it is moving, no, at a small velocity, no, because of its sheer mass. No. Now you notice that when these huge ships, no, like a cruise ship, no, that's a very big ship with so many passengers inside. No, once it passes on some small canals, no, like Panama Canal or Suez Canal, no, so they will be traveling at a very so slow velocity there. So they will have to maintain that velocity because in case there is no, a collision that will happen, then it will not really be so, uh, the damage will not be so big. No? Again, because the pathway there is so small, no, that uh, once they encounter a collision there and they will be trapped there, no, other passing vehicle or ships also will be affected. No? So the traffic there will be affected. So they try as much as possible to avoid, no, any collision or events like that, no, in some small passage, no, like those canals. No? So here we have a speedboat. No? So the speedboat will have a large momentum also, no, not because of its mass. No? Now, its momentum will come from its speed. No? So you'll see that there are some movies that when this speedboat, no, encounters a platform, it can go, no, it can go over it, no, because again, no, its momentum, ang iyang builos yun, no, will be too big, no, not again, no, because of its mass, but because of its speed, no. This one can travel so fast, no, in the water. No? Now I think now some of you who've taken a ride, no, with some speedboats, no, um, you will feel as though, no, you are passing, no, in a road, no. So, ang pamagtiyag mo sang dagat do dalan, no, do tiga siya, no, because ang impact sang ano na sang speedboat sa dagat, no, ang ginalampos-lampos siya bala, no. So you will not really notice, no, that it is a soft water, but it's very hard, no, ang water surface, no. That is if you have taken a ride, no, in a speedboat. Now to change the momentum of an object, no, either the mass or the velocity, no, is changed, or both, no, the mass and velocity are being changed. No? So that is to change our momentum. No? So we change the mass, no, or the speed or direction of our, no, our object. Now again, now to get our change. Now there's another concept that we will have here, no, that change in our momentum. No? So this is when we change the speed. No? So if you try to have an initial speed and then all of a sudden the object ends up with a final speed. No? Then since there's a change in the velocity of the object, then there's also a change in its momentum. So we indicate the change in momentum by this triangle. No? So you see a triangle with a letter P, no? That's read as change in P or change in momentum. No? So we can get that value by multiplying the mass of the object, no, times the final velocity minus the initial velocity of the object. No? So the difference, no, of the velocity is actually, no, the one that we refer to as delta V. No? Now delta, no, this triangle is read as delta, or the process there, no, in math is a subtraction process. No? So two velocities are being subtracted, no, from one another. No? So delta P, no? Delta P is known as the change in the momentum of the object. Now when we apply a net force on an object, no, we cause the object to accelerate. No? And we can probably recall that principle in our Newton's second law. No? F net, no, is equal to mass times acceleration. Now, the greater the net force applied to the object, no, the greater the change in the velocity, no, and hence, no, the change in the momentum also. No? So again, if you change the velocity, like you increase the velocity from an initial to a higher velocity, then there would be, no, a greater net force there. No? You have to exert a greater net force. No? And therefore, now there would be also a change, no, an increase probably in the value, no, of our change in the momentum. Okay, now let's try an example. No, try to apply the idea of linear momentum. So again, now if you recall momentum again, it's symbolized by letter P, and it is equivalent to the mass of the body times its velocity. Now let's try number one. Now, find the velocity of a 100-kilogram object traveling at a speed, or maybe a velocity of 20 meters per second. So all that we will do is to multiply the mass times its velocity, and therefore we end up with 2,000. So that will be 2,000 kilograms meter per second. That's our unit of momentum. So maybe now we can consider there an object that is probably moving from left to right. So if that's a velocity that has a specific direction. Now let's try number two. So continuing, so we have now a change in our velocity. So there is now a final velocity and there's an initial velocity. So therefore, from this next given or next number, we see that there will be a change in the momentum. And we will be using that triangle with a P, where we call it as delta. The triangle is called delta P. And again, delta P means maybe an initial linear momentum, then subtracted by a final linear momentum. So again, maybe final minus initial, or in other terms, that will be mass times the change in its velocity, or VF minus V sub I. So let's read the problem. So the velocity of a 2-kilogram object is increased from 2 meters per second to 4 meters per second. So we kind of double the speed of the object. So find the momentum, the change in the momentum of the object. So we will be determining delta P. And again, delta P will be m times delta V, or VF minus V sub I. So we have here 2 kilograms times the final velocity of 4 minus the initial velocity of 2 meters per second with a difference of 2 meters per second. So if you're going to multiply it by 2 kilograms, then you will have 4 kilogram meter per second value. So again, that's our change in our momentum. Now, the next concept that we are going to introduce is the word impulse. Actually, that may simply be considered as impulse. Now, usually, impulse is related to the change in the momentum of the body. Now, what is this thing, or what is this word that we call as impulse? Impulse usually is a result when maybe an object collides with another object. You will see that when a vehicle that is parked is suddenly hit by a moving truck or car, another. So there are two of them, one that is parked and one that is moving, or maybe a road post. So let's say, for example, there's a bridge, a flyover bridge on the city, and they have these structures that are placed in the middle of the road, and for some reason you lost control of your car and then you ram over this concrete structures or barriers on the road. Then you'll notice that there's a certain force that is created there. Now that force, when the car suddenly hits that concrete structure, a huge force is suddenly created. But that huge force will not be exerting itself indefinitely. It will only happen for a fraction, very, very small unit of time. And however, that force is so huge, and we know that it's very huge because after the vehicle collided with those permanent or those concrete structures or barriers, the vehicle will be literally damaged, or the vehicle will be completely inoperable anymore. You cannot use the vehicle anymore. It will be a total wreck. If in case the car is running at a very, very fast speed. So again, that huge force that is suddenly created when something rams over a fixed structure like a concrete is known as impulse. Now, that force is suddenly created, and it's enormously large, and acting, however, on a very, very short period of time. Okay, so again, that's what they call impulse. And this thing called impulse is a value that we will label with letter I, and it's a product actually of the force that was that results of the collision and the time it took for that force to be created. Now let's look at the concept of this moment of this impulse. So again, impulse usually is a direct result when there's a change in the velocity of the car. So again, something that is running, all of a sudden it stops moving because it hits a certain barrier. So it is a change of the velocity from moving to a complete stop. So if you suddenly stop the car, then maybe the force that you will have to create to make it stop immediately will be enormously large. And usually, when they test some safety level of a car, like how good is a seat belt, how can it protect you, or that bag there, that airbag that is in front of the driver, how will it suddenly deploy? Will it be quick enough to keep the driver from hitting the dashboard in the event of a collision? Now all that is taken into account when again that huge force suddenly is created, and again you will not have time to react. So I don't think that when such a collision will happen, you will have the opportunity still to hold on to railings or to handles in the car, because it will happen in a very, very quick manner. And that is why we are always advised to wear a seat belt, because that seat belt will always lock itself, and that will keep you from ramming on the dashboard or hard objects in your car. Again, because of that sudden huge force that results. So again, that's a sudden change of velocity from moving to a complete stop when you hit an object that is literally like a concrete on the road. Now, the amount of time a net force acts on a body will make a difference in the change of its momentum. So again, when the time is very short, then the force that results is so big. But if the force is not so big, then probably the time that it occurred may probably occur on a longer, in a much longer period of time, considering about impulse. So impulse can be varied by two factors again, force, external force, and another is the time for that force to be created. Now, we have a car here now. It's stalled. Hindi na siya mag-andar. So what do? Usually, you try to give it a push. So this car, if it will take a long time for it to move, so maybe you'll be applying the force there relatively longer and lesser force. So the lesser force that you apply for you to move it will take a longer period of time to be applied. But if this car will suddenly move very, very quickly, and maybe the force is so big, and that's why it only took a less amount of time for it to move. So change of its velocity can occur when there's impulse. Now, however, if the same magnitude of force is applied over an extended period of time, greater change in momentum will also occur. So again, in this case, we did not apply a huge force because there's only one person there pushing. So that person will push that car for an extended period of time. Now, let's look at the relationship of Newton's second law to what we are talking. So if we will try to recall the net external force F, then that's equals to the product of M times A. Now, if A, again, is BF minus BI all over T. So literally the numerator BF minus BI is a change in the velocity. Now, cross-multiplying our A and substituting, the value of A, which is delta V over T, to our F equals MA equation, then we will end up with F equals M times delta V over T. No? Now, if you try to cross multiply F and T together, no? So you'll get FT. And what remains on the right side will be M times delta V. No? So sorry, no, this is not delta T, but delta V na sana. So it must be delta V. No? So again, now what happens is that we will have here Ft no, times M no, delta V. No? I'm making a little correction here. No? So please change delta T here. No? That's not delta T. No? Looking at our equation above. So that's M delta V over T. No? So if you multiply both sides by T, no? So that will now, this one now cancels out. And then therefore it leaves you with Ft M no, times delta V. No? So again, I will repeat that this must be no, delta V. No? Okay, so that's again, Ft equals M times delta V. No? Okay, the product of F times T is now termed as impulse. No? So the product of the force times time. No? So if it's force times time, then you have a unit there, Newton second. No? Newton times second. No? And while the other side no, may somehow, no, it will also have a similar value. No? So it will be kilogram meter per second. Or you can also call it as Newton second value. So the product of the force that is created when once there's a change in the momentum of the body no, is known as your impulse. No? The impulse again is the product of the force times the time. And it is also defined as the change of the momentum delta P. No? So we give it a name earlier. We call it as delta P value. No? So the unit of impulse is this. No? So Newton second. And our change in momentum is delta P now, or that's M times delta V. No? Ang ating na change of the momentum. Now, the change of the momentum is equals to I no? Or to Ft. No? Now, the momentum of an object can be lessened no? In two ways. No? Number one, by decreasing the force no? Over a long period of time. No? So if you reduce the force and you extend the time, no? maybe now you'll be able to decrease the momentum of the object. No? By decreasing the force over a short period of time, no? Will also no? Change the momentum of the body. And here are examples that you can likewise try. Okay, so I think for number one, no, we can find there the impulse by simply multiplying the force multiplied by no, our value 10 seconds. No? So our letter A will be 500 no, Newton seconds. No? Now usually the change in the velocity of the object no, will be equivalent to delta V. No? And for letter B, no, I think we can find the change in the velocity no, by dividing the impulse by the mass. No? So impulse over mass gives you the change in the velocity of the object. Now here are other numbers that you can try no, for this given no, problem. Okay, so that's our last slide there. No? And that covers our topic no, for today. No?